Hello everyone, Kotongwane, the Nated God here. We are still on forces, but we are going to look at a scenario where you have a system of forces that are keeping the system in equilibrium, and then we use the conditions of equilibrium to calculate the unknown forces, right? But before we get to this, let us first look at 3.1, define parallelogram of forces. Now, parallelogram of forces, right? This is how I've defined it, right? But what is important is understanding how you go about using the parallelogram of forces, right? Parallelogram isn't necessarily a parallelogram of forces, right? It's essentially a parallelogram of vectors, right? Because we are able to use the parallelogram method for any vector, right? Including velocity, displacement, right? So whichever vector or whichever vectors the problem is based on, yes, right? So for this module in particular, it is based on forces, right? Maybe that's why they've stated this the way they have defined the parallelogram of forces, right? But just to be clear, it's actually the parallelogram of vectors, because this method, like I said, you are able to use with any and all vectors, right? Now, the parallelogram of vectors essentially, right, you are able to use only if the body you are looking at or the problem you are looking at is based on two forces being applied, or a body being subjected to two forces, right? Let's just borrow this Cartesian plane, right? So say you have two objects. You have an object and it is being subjected to two forces, right? One of the forces is headed, say, in this direction, right? And the other one is headed, say, in this direction, right? Okay, let's make this one slightly longer. Right, this is fine. So that's going in that direction, and this one is headed in that direction, right? So when you draw them on the Cartesian plane, you draw them headed in their respective directions, right? You have two vectors that a body is being subjected to, right? So the way you use the parallelogram is by completing a parallelogram, right? And to complete the parallelogram, right, you would have to say draw a small Cartesian plane there, right, so that you are able to draw this vector at that point, right? Now I'm not going to go into much deeper details, right, but this is just to show you how you go about using the parallelogram method, right? You draw a small Cartesian plane there and you draw this vector, right? This vector is headed in that direction, and then you then draw another Cartesian plane at the end of this one, right, to draw this vector, right? At the end of it all, you get something that looks like this here, right? And this here is referred to as the parallelogram, right? So we use the parallelogram, right? It is a vector diagram or a graphical method that we use to get the resultant, right, of the two forces acting on this body, right? And they will go in that direction, right? And this completes your parallelogram essentially. So the parallelogram of forces, right, or vectors, is a graphical method that we use or that we can use when two vectors, right, are acting on a body, or let me say for this case when two forces are acting on a body. So we use the parallelogram method, right, to have an idea of where the resultant force is going to be acting, right? And that is what a parallelogram of forces or a parallelogram of vectors is essentially. Right? It's a graphical method that we use to determine the resultant, right, of two forces that are acting on an object or a body. Right? Now, you can draw the parallelogram graphically using a scale, of which if you use a scale, then you use your scale to determine your resultant, or you don't necessarily have to use a scale for this, right? If you haven't used a scale, then you make use of the sine rule or the cosine rule, right, to determine the resultant, right? Now this, you are going to have to, or you are going to go deeper in when you get to N4, right? When we do a module called kinematics under engineering science, right? The sub-units of that module, resulting velocity as well as relative velocity, and projectile motion, but we get to use this method, right, for resulting and relative velocity in particular, right? So that is when we'll get deeper into it, right? But just to answer this question, right, the parallelogram of forces or parallelogram of vectors, that's what it is, right? But you can use this definition, right, to define the term parallelogram of forces, parallelogram of vectors, right? Now, let's look at 3.2. Determine the magnitude of the unknown forces. The unknown forces shown in the system of forces in figure 3. Right, so this is what they're talking about. Right, so I would say that this hasn't been phrased correctly, right? Because nothing in the statement gives us an idea that this system of forces are in equilibrium, right? For us to be able to solve this, they would have to tell us that this system of forces are in equilibrium, right? But just so we are clear, as much as they haven't stated here that the system of forces are in equilibrium, for such questions where you have unknown forces, right, we always assume that the system of forces are in equilibrium, right? So we apply conditions of equilibrium, knowing very well that the system of forces are in equilibrium, meaning that the vector sum of forces here is equal to 0, right? Unlike with the first scenario, which we did before this video on the playlist, right? Now, they want us to determine the magnitude of the unknown forces, right? So the unknown forces is L and M, right? And they want us to determine the magnitude of those forces, right? So we are going to do that applying conditions of equilibrium, right? Now this you can do, so say this is on your question paper, you can simply do this on your question paper quickly, right? What I'm about to do, redrawing the vectors, right, on the Cartesian plane, so that we're able to resolve them into its components. The reason why I'm going to redraw them is because if you look here, we have two vectors, right, that are pointing towards the point of intersection, or that are pointing towards the point where all of these forces coincide, right? Coincide, right? If you don't know what this term means, look it up, right? But that is how you spell it. So if you look here, we have two forces, the 80 newtons and the M, pointing towards the point where these forces coincide, right? Now, in problems based on the application of conditions of equilibrium, right, if you have coplanar and concurrent forces, right, you must always make sure that in resolving the forces into its components, right, in having to apply the conditions of equilibrium, you must make certain that all of the forces are pointing away from the point of intersection, or away from the point in which the forces coincide, right? So I'm going to redraw the vectors, making sure that all of the vectors are pointing away from this point, right? So we have the 70 newtons, right? You have the 70 newtons. It is headed in that direction. It's making an angle of 45 degrees with the horizontal. So you have 45 degrees here, right? This is 70 newtons, right? So that's 70 newtons, right? Now this is in the first quadrant, therefore when resolving it into its components, this will be the direction of the two components, right? So our angle is referenced from the x-axis, therefore the vertical component will be in terms of sine, and the horizontal component headed east, positive 70, will be in terms of cos 45, right? And then you get, right, so you get this 80 newtons, right? If you look at the 80 newtons, it is headed towards the point of intersection. You must draw it going away from this point, right? So the direction is west. So all you do here is draw this heading west, right? You draw this heading west, right? So you see now it is heading away from this point, right? So it's headed west, so you take it as being negative 80 newtons, right? And then you have the force L, right? The L is in this direction. We are going to use the angle reference from the x-axis, and that angle is 30 degrees, right? So this is going to be somewhere here, right? Making an angle of 30 degrees headed in that direction. So this is L. Now L, force L, is in the fourth quadrant, so its components will be headed in these two directions, right? So the horizontal component headed east, so positive L cos 30. Its vertical component is headed south, so it's going to be negative L sine 30 degrees. All right. Next one is the 50. Right, so you have the 50 newtons. Right, it's headed in this direction, also in the fourth quadrant. Right. Now the angle we are going to use is reference from the x-axis. So from here to the x-axis is 30 plus 30, which is 60 degrees. So this one is somewhere here. Let's just say somewhere here. It's headed in that direction. And then this angle is 60 degrees. That's from here to there is 60 degrees. Right? And this is 50 newtons. Right, so this is still in the fourth quadrant, therefore the components will be headed in this direction. Right, horizontal component is headed east, so it's positive 50 cos 60. Vertical component is headed south, so it's negative 50 sine 60. Right, done with that. Now we look at force M. Now force M, right, is headed upward. Now it is heading towards the point of intersection, so you must fix that and draw it going away from this point. So you simply are going to draw it heading north, right? So on the upper end of the y-axis, right? So this is headed in this direction, right? And there you have M, right? Now this format is correct. Why? Because all our vectors now are heading away from the points of intersection, right? Now you can apply conditions of equilibrium. Yes. So in applying conditions of equilibrium, let's say the sum of forces in the x direction is equal to 0. Now we know the sum of forces in the x direction are equal to 0, right? Because like I said, for such problems, even though in this case they didn't tell us, it is wrong that they didn't tell us, they should have, right? But in such scenarios where you have unknowns, right, they always tell us, or we always assume that the system of forces are in equilibrium. If they are in equilibrium, it means the sum of forces in the x direction are equal to 0. Also, the sum of forces in the y direction are also equal to 0. Now, we add up our horizontal components, right? So you have the 70 cos 45 plus the negative 80, so negative 80 plus next force is L. Component of L in the x direction is positive L cos 30 plus the 50 cos 60. Right, all this is equal to 0. Right. Now, obviously, if you look at this algebraic expression, you only have one unknown. Right. So we add the what is this? We add the like terms, which is this term, and this term. Right. And then this one, cos 30. If you punch that in your calculators, you're going to get 0.866. So times L. Right, and then if you add these like terms, you are going to get negative 5,503. All of this is equal to 0. Right, we are looking for L, so we transpose this term to that side, of which it will become positive. So you'll be left with this is equal to positive 5,503. And then because we're looking for L, you then divide both sides by 0,866. You need to divide this side as well by 0,866. That cancels. And then L will be equal to, if you punch this in your calculators, you should get 6,355 newtons. Right, and that is the value of L. Right, now you apply conditions of equilibrium in the y plane, in the y-axis. So sum of forces in the y direction is equal to 0. Now you add all forces in the y direction. Right, you have the M, it's headed north, so you take it as being positive M plus positive 70 sine 45 plus negative L sine 30 plus the negative 50 sine 60. All this is equal to 0. Right, so again here we have essentially one unknown because we already have the value of L. Right, we already have the value of L. So because we already have the value of L, right, essentially what we have here is this plus negative L. L is 6,355 sine 30 plus this, right, is equal to 0. Right, so at this point it's now clear we only have one unknown, right? So if you add of this up, so M remains the same, and then if you add that up, the like terms here, you should get positive 3,019 is equal to 0, right? Then to get M, simply take this term, transpose it to the other side, and you'll be left with M is equal to, now this becomes negative 3,019, which is actually 3,019 newtons, right? This is negative, right? And remember, this is parallel with the y-axis, so because it's negative, it actually means this is headed south, right? Now initially you were told that this is headed north. That means this assumption is wrong, right? For this to be in equilibrium, this has to be headed south, right? That is all what this means, right? The math does not lie though, right? So M is actually headed south, or perhaps there was a mistake here. I have no idea. Maybe there was a mistake. This was actually supposed to be pointing downwards. Either way though, right, when that happens, you just correct it mathematically, right? The math doesn't lie. So all this means is that M is actually pointing downwards, right? It is pointing downwards, right? And that is how you would attempt such questions, right? Applying conditions of equilibrium analytically, right? Now let's look at 3.3. Name two conditions of static equilibrium if forces acting on the framework or object are in equilibrium. Right, so 3.3, right, these you should already know, right? Static equilibrium, sum of forces in the x direction equal to 0, sum of forces in the y direction equal to 0, and then sum of clockwise moments is equal to the sum of anti-clockwise moments. Right, so this one is based on the law of moments. Right, the law of moments essentially states that for a system that is in equilibrium, the sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. Right, that's the law of moments. They only wanted us to state two conditions. You can state any one of these and they would be correct. Right, hope you found this video helpful. Right, stay tuned for more videos, more content on engineering science and 3. Right, Nature God signing out.